All right, so welcome everyone. Today we have Tony Rieser telling us about, what's that thing, Tony? Sheaves for data and graphs through check closure spaces.
All right, so thank you very much. Let me just have this thing here. Okay. So thanks to everyone for the invitation. It's a pleasure to speak to your seminar. So I'm going to speak today about two things, actually. So first, I'm going to give kind of some an introduction to why, or to a perspective I've been developing for how to kind of reunite algebraic topology and homotopy theory with applied topology. Here, data is just going to be finite metric spaces. So I'm going to abstract away anything nasty about data. It's always going to be finite metric space. And our motivating question really started with a misreading on my part, or not misreading, but an incorrect impression of what algebraic applied topology was going to be. So I didn't start out as an applied topologist. I was a symplectic topologist for a while. And I think, you heard about applied topology kind of in the background. And I always thought it was going to be something like, I have my space of data points, and we have some topological space, and I want to use the data points to estimate the algebraic topological invariance of the topological space. And to a degree, that is sort of one of the questions people think about, but not as much as I would have imagined. And so I decided to take that seriously, and what I'm going to talk about is kind of the result of that question. So what goes wrong when trying to do this? It's sort of obvious, right? You have maps. Suppose these points actually came from this space, right? So it's actually a subset. So you have a map, an inclusion map into here, which is fine. But we don't have a good map in this direction. Right? And that indicates that perhaps we need to leave topological spaces. We need to add some more maps. And so the first part of the talk will be asking what kind of maps, what kind of extra maps do we need? So one of the constructions one does find, though, is just what's called the Viator search complex. Or homology at a scale R. So I'm going to take my generally finite, but it doesn't have to be, my metric space. So and I'm going to create this simplicial complex such that my simplices are going to be just finite collections of points in the metric space, if and only if the diameter of all of those points is less than or equal to R. And then, you get some invariant, whichever your favorite invariant is, by taking the homology or homotopy or cohomology, whatever you want, of that simplicial complex. So this is a nice construction, actually, and there's some nice properties with it that come with it. For instance, so it was shown a long time ago, even before 2001, that if you start with the Riemannian manifold, and I have some set, can be finite, can be infinite, whatever, so that the Gromov-Hausdorff distance, this is also a metric space, of my manifold, my set, my other metric space, is less than, say, something small. Hold on. Then there exists some radius so that this vector Sheaves complex, for anything smaller than this radius, is homotopy equivalent to the original map. And so this tells us that this original question actually isn't hopeless, but it does have a curious shortcoming, which is that this first construction, so going from X to the Beatrice-Rich complex, is functorial in a very kind of unsatisfying way. So there is it is functorial somewhere. So if I take X, I go to R, X. So this is functorial functor from, usually it's called CIMAT, metric spaces with okay, I mean that's fine, but it begs the question, we work in category theory because we believe the maps are what's important. So do we really think that contractions are what we want to study? And I think the answer pretty much has to be no. We're still looking for something else. But this does tell us what this something else should be. So these one-Lipschitz maps, the problem with them is that they're too global. So we would like R to indicate local structure, but nothing global. And so instead of putting my scale into the functor, I'm going to attach it to the space. And then I'm going to change the notion of continuity in the following way. So let's say function P between two metric spaces and two scales. So this is some number, this is my metric. This is a number greater than or equal to 0. Is, we'll just call it PQ continuous, might be better. If and only if, and let's change a little the standard, epsilon delta definition of continuity. So for every epsilon 0, it's just a delta greater than 0, such that should be, so dx less than p plus delta implies dy is less than p plus delta. Okay. So now, remember this first example. Let's see what happens. If I turn p into 0, and I make q kind of medium size, not too big, not too small, then I actually have a pretty good map from this space to this space. In particular, I have what you might call the nearest neighbor map, where you take every point from here, or you take points from your circle and you send it to the nearest one that's part of the subset. And so that's now continuous in this sense. Surprisingly, this notion of continuity has actually been not exactly studied in this form, but is part of continuity of what's called check closure spaces. So let me explain what that is. So closure space, check closure space, it's a pair, X is a set, and C is a map from the power set to the power set. Such that C of the empty set is the empty set. It's finitely additive. And expensive. One, two. Now, if you've seen the closure version of topological spaces, notice that I omitted number 4, which is that C of A, C. So for all subsets of X, C of A equal to. Okay, so if I add this 4th axiom, then I've just redefined topological spaces. But if you get rid of it, then you have a lot more flexibility, and we can capture the kinds of spaces and structures that I was talking about a second ago. And then the notion of continuity here is just the closure space notion of continuity of non-closure spaces. So X, C of A, and C.
Antonio,
Yes.
sorry, can I ask you to reproduce the condition 4, which would have made it coincide with topological spaces? I saw it for about half a second.
Pardon?
Could you write down the
Yeah,
condition
sure.
4 that made it coincide with topological spaces again?
C of A is equal to the square. That the closure of the closure is equal to the original closure.
Got it. Okay, thank you.
Tony, can you give us some like natural examples that are not the closure or like the identity or something?
That are not, yeah, sure. So, so the first set of examples are just the spaces that, so suppose you have a set, a metric space, and some scale, then our closure of the set will be all of my elements. So I'm going to thicken A by P. Right? So all the elements of X, such that the distance between X and A are less than equal to P. And when I get back 0, then you get back just the standard topology. But when P is non-zero, then you have something that's not topological, and that is a closure space. The second example is graphs. So if I have a graph, you can actually fit it into here as a metric space, but it's nice not to have to think about it like that. So if I have a graph, then my closure of a point is just going to be the star of the point, and the closure of some subset will be the union of the stars in that subset. Right, so again, I'm just thickening the graph or my set by 1 step. And in both of these examples, the indication that I'm getting things, at least if not right, on the right track, is that functions here, this is going to be my first dilemma, is that functions here, is QR continuous? Oh, no, that's fine. QP. If only if F is continuous closure space. Right, so these two notions of continuity coincide exactly. Similarly, in the graph case, this was noticed actually a long time ago by Maria and Megan, again by me, 80s. That, again, if I have a graph homomorphism, a reflexive graph homomorphism, so what this means is that I'm imagining that I always have loops on every vertex, and that this is a normal graph homomorphism, or you don't imagine the loops, but you allow the map to collapse edges. Right? I don't know if that's equivalent. This is a reflexive graph homomorphism if and only if F is closure space relative to the closure structure. Okay, so this is very nice. You can do a certain amount of homotopy theory with this. Unfortunately, not too much. Because, so flaw is that closure spaces are not Cartesian closed. But this can be fixed by putting it into yet a bigger category, pseudo-topological spaces. Not going to tell you about. Which contain closure spaces as a full subcategory R. And here we have and theorem exist equivalent monocategory structure here on okay, this is B and also actually this was so I did this sort of by hand, just rerunning equivalence proof, and they have a very slick proof for the same result. So, and so pseudo-topological spaces, we have this nice category where we have good notion of homotopy and a lot of theory, good model category, and then also captures graphs and these funny spaces with scales as well as topological spaces. And so it seems like, all right. So I advertise this as a Sheaves talk. So let me get change gears a little bit. Pseudo-topological spaces are a little bit technically annoying because they're defined via, so I'm not going to put the definition down. They're defined via ultra filters. Once you get used to it, it's not so bad, but you know, at first it's not so nice. Enclosure spaces are definitely simpler to think about and work with. So towards Sheaves. Okay.
Can I ask, do these closure spaces form like some special class in your model structure of pseudo spaces?
I don't know. Not that they're kind of so there's nothing like, for instance, you know, compactly generated house source spaces in closure spaces. So they're sort of or at least There could be, but they fail to capture the examples we want to capture. So, yep. Yeah, so it really seems like we need to generalize in order to do a double table. It'd be nice if that wasn't true. At the moment, it seems like. Okay, so sheaf theory. So one nice thing about closure spaces is that they're completely structures are completely determined by what are called neighborhoods around each point. Okay, and in order to make sense of this statement, I'm going to have to go through a couple definitions. So first, what's a neighborhood? So I have closure space, a set here, another set is a neighborhood of A. So if A is a subset X minus the closure of X, the complement. So it's the complement of the closure of the complement. And if you sort of play with this, this is exactly also the closure space definition of the interior. Of a set even in topological spaces. So now, what can I do with this? Well, now I have a notion of neighborhood. There's also a nice notion of interior cover. Of X. If and only if what? So what I expect of the union of the interiors of these guys, right? The cover the space. Let's do a couple examples there because it's instructive. It's fine. Let's go back to graphs. And I'm going to claim first that the star of any point is a neighborhood of that point. In fact, it has to be a minimal neighborhood of that point. And so let's just do that, right? So let's take this point, this star, these guys. The complement is everything outside. The closure of the complement will kill these points. And then the complement of the closure of the complement is exactly my original point. So this gives me, so this point is in fact, it's equal to the interior of its star. So now an interior cover of a graph is just going to be the collection of all of this, well, the minimal interior cover of a graph with a collection of all of its stars. Okay. So now we almost have what we need to, I'm going really fast. So something I can, oh, it's fine, okay. For sheaf theory. So how would one want to redo sheaf theory here? So we take, maybe instead of open sets, we could take sets with n. And then as a pre-sheave, we would consider this with inclusion. Because there's a problem here, which is that this collection isn't closed under intersection. So it gets very easy, in fact, in my original example. So this just erased. So if I take the star of some point, I take the star of some other point, say this one, the intersection is just this one point. If you work out the definition, the interior of that point is the empty side, right? The interior of that intersection. So I can't use this. So you might do the silly thing and just add them all back in. Let's take NX. And this takes care of the first problem, but it creates a second problem, which is that there are too many of these guys. Right? So now, in fact, MX is a topology. So the NX is closed under arbitrary unions. Now I've added back finite intersections, so I get a topology. If I just do normal topological sheaf theory here, I get something that's way too fine. So exactly for the reason that I said before. So if I look at the set, and this set. So these single point sets end up being in my space, and my sheaves very often, much more often than I want, are just going to be sheaves over sort of discrete collections of points, which is useless. Okay. So we need something in between. And growth indeed kind of tells us exactly what it is we need to do. So the solution. So we're going to use MX as our base category. But we're only going to take covers that are interior covers. And first and theorem is that this is sensible. So interior covers form spaces of the growth indeed category. Growth indeed topologies. What is growth indeed topology? Basis again. And I'm not going to define growth index topologies because it's sort of a nest of definitions that I don't want to get into, but I will look at what a basis is. I'll put the edit in my notes. Okay. So if I have some category of pullbacks, And I'm going to take C, let's see, K, sends every object to a collection of morphisms, or various ways you can say this. Sure. With the original code I made. Such that three things are true. First, the isomorphism is there. Two, if I have some collection, and I have some other, suppose, in KFC, and I have a map from D to C, and the pullback of this collection is going to be in KFD, pullback. And the last one, a little bit tricky. So right. And then I want composites, right? So third is that I have some collection here. See. And I have some other collections. Then I can compose them when I get back something in QC. Okay. The only tricky bit to show that we have growth in the category, so this is pretty much automatic, is number 3. And the reason it's tricky is because when I move levels from here to here, also the notion of interior changes. So I'm here, my interior cover, these covers are taken with respect to the interior on C, whereas in all of these, the interiors are taken with respect to the interiors on CI. And so you have to show that the Ds are forced to be big enough so that the interiors taken with respect to C actually cover C, right? And that ends up being true. Okay. I'm going way too fast. Okay. So now we have Sheaves, or growth and decomposes anyway, and Sheaves on closure space. We do all the fun things. Come on. So one of the things that one might like to do with this is to have a presentation of these sheaves as sections of some étal space. That doesn't quite work here, so we have to change this. The sheaves. The issue is the same thing. So what's our candidate for the étal space? So we want to look at stocks. What would that be? That would be the X, might be the limit, as in, you know, the neighborhood Yeah. This is a perfectly reasonable definition of a stock. But there's a problem now, again, related to this issue of the changing interiors. So in MX, I have a whole bunch of spaces, subspaces of X. The neighborhood of X now depends on which subspace I'm taking as my base. And so instead of just having one stock, I have a stock for every space in here. Let's say B is in the neighborhood with respect to U, and now I look at limits. So now I have, you know, instead of one space, I end up with a whole bunch, and I have to put them back together in some way. And the way we're going to do this is by, we call it a tile system. I'm going to take this collection. CEU. I have some collection of closure spaces. I have projections, and then these are going to end up being restriction type maps. So that is here. Is an tile system. Yeah. Two things happen. First, this is continuous. It's a local isomorphism. For all U. And second, following thing is true. So suppose we have two these two will fit into the following commutative diagram. So I have U begins here. B. And here's my this map that I require to exist. I have U. And then my inclusion map. Okay. And so I require that these maps will fit into commutative diagrams like this. This seems a bit exotic. These things actually show up. So one of the possible, you know, an example of pre-Sheaves anyway, is if you have a graph, a bunch of nodes, and then you suppose that any that you look at a collection of words where the letters of each word are indexed by the nodes, right? So, and then our restriction maps will be now the possible collections of words you get when you restrict the nodes. If you look at what happens on the space of words, you actually end up with something very much like this commutative diagram. This is actually not so exotic. It also turns out to be a good notion, exactly for the following. that every sheaf, so if the other thing that's extremely convenient is that these guys, the sections here, the continuous sections here, are not necessarily a sheaf, but they are pre-sheaf at least. But if I start with a sheaf, it's a sheaf, then F is isomorphic to the sheaf of sections. I should say then pre-sheaf. Of the Excel system. And like this, here's the sheaf, and F is isomorphic to the sheaf of sections. All right, so modulo this kind of computation, we do have a nice representation of sheaves in terms of sections over some collection of spaces. Maybe not as nice as in topological spaces, but at least something. I think that's about all I'm going to say. All right, so I'll make a couple of remarks just to end. So first, something that was perhaps not obvious from the examples that I gave, but that directed graphs also don't induce closure spaces. And so this construction gives a nice construction of sheaves starting with directed graphs. And I think it's the only one I know like that. Maybe this one. Maybe not. Second remark. So this reduces the sheaf homology. For topological spaces is isomorphic to sheaf homology constructed here. So this is seen as a closure space. And that follows pretty simply from the fact that open sets or open covers end up being a cofinal subcollection of the interior covers. And computations are ongoing, or that's the part that's still in progress, I guess. But I expect that I expect to find examples of graphs which have non-trivial higher dimensional, greater than one dimensional sheaf cohomology. So the idea being that you really want to use these graphs as representatives of some other topological space that may not be one-dimensional. And if those calculations turn out to be the case, this seems to be a reasonable thing to do. I think I'll end there. Yeah, great. Thanks very much.
Do you have any questions or comments for Tony?
Can I ask something? So I'm not saying I lost track of all the details of what you were saying, but do your sheaves in your context, do they behave like the usual sort of sheaves? Like, is there a sheafification functor, and do sheaves form an abelian category and things like that?
Right. So once you have the growth ending topology, you can use the entire machinery of growth ending topologies. So you have sheafification and sheaves to abelian groups or an abelian category or to modules, whatever. So yeah.
And you were saying that, if I understood correctly, a hope is that given a space, you'll be able to find some like graph inside of the space that reconstructs the same sheaf cohomology as the space?
That's the hope, right? I think in general, probably that's too ambitious, but for spaces like manifolds or maybe even stratified manifolds, that's the conjecture.
Interesting. Like a finite graph?
For compact manifolds, yeah.
I have zero experience with these kinds of reasonings, but like, is there a way to give some intuition as to why that would be feasible?
So yes and no. So I'm hoping that the standard. All right, so a certain amount of the standard machinery relating sheaves to check homology goes through, right? The problem is not quite enough is obvious to make the stronger claims, right? So my hope is that can be worked around, and at least the check cohomologies is fairly easy, at least on say, constant sheaves, is fairly easy to compute. You just literally just pick one of these minimal interior covers and then compute the nerve. So these guys do look like manifolds in nice situations, and one hopes that as you move over to sheaves, not too much gets messed up.
That would be pretty.
You might fail, but
Do you have any other questions?
What about constant sheaves? Do you have other constant sheaves, and can you just recover the standard cohomologies theory, like with coefficients in abelian groups, for example? If you use if there are constant sheaves of abelian groups, and will they satisfy any of the Eilenberg's Tudor axioms?
So there are definitely constant sheaves to abelian groups. I don't know the properties yet, but I expect that that'll be true. Certainly, check cohomology works very nicely and satisfies all the axioms. In fact, one of my students, it satisfies all the axioms minus excision, but I think that's because there's a funny thing in how he defined it relative to multiple, but we're working on that. But on the sheaf side, I haven't confirmed. I haven't checked it yet. So, but the expectation is yes. Certainly, constant sheaves exist.
Yeah.
Nice.
Very good. practice, would you be more interested in a local systems, like locally constant sheaves, or what kind of sheaves would you be, would be more useful?
So-
In
Well,
applications?
in applications, it's hard to say. So one of the example that I'm quite interested in is exactly what I alluded to before, where you have some network, you know, every node on the network has some allowable states, but sometimes they're correlated and sometimes they're not. And then you ask, well, does the set of words that you get from this network form or induce a sheaf on the network, and is there topological information there? So this is sort of the application that we're heading toward. And I had in the back of my mind when I was.
Thank you.
No other questions? Then let's thank Anthony again.
Thanks a lot.